when you're ready. Okay, so let me try again. So we are going to have Professor Amir Schikorra from University of Pittsburgh to speak today. And his title talk is on Calderon-Zygmund Theory for the p-Laplace. So I give to you, Amir.
All right. Thank you very much. Thanks everybody for coming. Thanks for having me. So I want to talk about something very classical. Calderon-Zygmund Theory, well, for the p-Laplace. So let me start with the classical Calderon-Zygmund. I assume that we all know what it is, but just to get into the topic and fix some notation. Oh, my hand is over the camera. Okay. So Calderon-Zygmund estimate for the Laplace, right? Very, very classical, 1950s, I guess. We have something like Laplace u equals the divergence of a vector field, capital F. Then we get that the LR norm is under control in terms of the LR norm of the right-hand side, right? Why is something like this true, right? The numerology, which will be important for the p-Laplace, so let's do this now. You write this Laplace u equals divergence of F. The Laplace itself is the divergence of the gradient, okay? You kind of formally invert the divergence, which of course is a little bit illegal, and you kind of assume that the gradient behaves like this F, right? And this roughly, suggests that such an inequality might be true. Maybe this is why they first started to prove this. Of course, this is not really the proof. This is wrong. Also, the statement is completely wrong, right? So you can plug in polynomials and you see that you have no such inequality. But philosophically, the statement is correct. Okay? So what's actually the correct statement? We kind of need to rule out polynomials, right? So polynomials are bad counterexamples. So in this case, it's like linear polynomials that we want to get out. So we usually assume something like Sobolev on Rn, including like an L2 assumption. So polynomials are not permitted to be in the space except if they are zero. Then if the Laplace of u is the divergence of the vector field F, we have that the gradient of u in the LR norm is controlled by F in the LR norm. Okay? And the actual proof is a bit more complicated, but I assume that most of you kind of are very familiar with this. I want to go through this just to put this into contrast with the p-Laplace situation. So the way you prove this inequality, the simplest way I would say, is you get a representation formula. So you write Laplace equals divergence of F. Divergence cannot be inverted because it has a big kernel. It's not invertible, but the Laplace is an invertible operator, and we have a very nice formula for it, right? So we can write the solution to this equation, since we ruled out polynomials, as u is the Laplace inverse of this divergence. Now we are interested in the gradient of u, so we take derivatives, and so what we have is that the derivative of u is the derivative of the inverse Laplace of the derivative. There's a commutation. If you take Fourier transform, for example, you can switch over these things, and you have this sort of representation. You have an equality. And now, this Laplace inverse, of course, is exactly known what kind of operator this is. This is the Riesz potential, or the Newton potential in this particular case. Let the dimension be 3 and higher, just for simplicity, so I don't write the logarithm. So the inverse Laplace has the formula, it's the Riesz potential, x minus y to the 2 minus n, then the right-hand side. So this object here has a precise formula that we can just compute, right? So the gradient of u is 2 derivatives of this guy. The kernel here is homogeneity 2 minus n. So after taking 2 derivatives, whatever comes out, the homogeneity will be like n, negative n, right? So we can write the derivative of u as this sort of integral, right? Where this k is something zero homogeneous, like an x over mod x type of object, applied to the right-hand side. We sum a little bit over these repeated indices if need be, but this is the structure of the solution. And now we just need to show that this operator is bounded or continuous on LP spaces, right? And this is this theorem by Calderon-Zygmund from the 50s. Such operators, there are some assumptions on K, of course, right? But they're kind of zero homogeneous and suitable decay. These operators are just bounded, so continuous linear operators from LP or LR to LR, and this implies this inequality up here, right? If this is a bounded linear operator, we have this Calderon-Zygmund theory. All right, very classical. Of course, this is where some work has to go into, but the point is, for the linear PDEs, we just have a representation formula, and then we are kind of almost done. Okay. So I want to just reformulate this so we're on the same page on a ball, and then I move to the p-Laplace. Okay, so on the ball, you need the Green's formula, so it's a bit more annoying to prove, but you have the same statement. You rule somehow the polynomials out. So say you are on the ball, and on the boundary of the ball, you say that u is constantly 0. Then you have that the LR norm of u is controlled by this vector field in the same norm. Okay, so that's the classical, what I want to refer to as Calderon-Zygmund. All right, now we want to do the same for the p-Laplace. Sorry, before we do this, you can, extend this into a bunch of directions, right? So the first easy extension would be make a very smooth change of coordinates. So put some A, which is somehow the metric of a space, so it's symmetric, say all eigenvalues bound away from 0, so very elliptic. If it's Hodder continuous, you just run the same sort of argument, maybe a little bit of iteration to get such estimate. If A becomes in BMO, it gets more fun, right? Then you have such an estimate as well. If A is just bounded measurable, this estimate starts to be wrong, okay? You can also kind of change the omega, especially if the omega becomes something crazy. You can work on this, and this is still, I guess, there's some open questions. But what I want to move to is the p-Laplace. All right, so let's look at the p-Laplace. Now, the p-Laplace, my understanding, I'm certainly not an expert on this, kind of became popular in the 80s, right? And the question is essentially just, can we copy such a result for the p-Laplace, right? So the p-Laplace, the normal Laplace is the critical point, or the operator, the first derivative of the Dirichlet integral, and the p-Laplace just replaces the 2 by a p, compute the first variation, and you see that you have this operator. It's pretty complicated because, it's nonlinear, right? Leading order guy is nonlinear, and it has this weight, right? This weight is kind of degenerate or singular, but if the gradient of u is 0, this guy doesn't have ellipticity unless p is less than 2, and then it has a lot of ellipticity, right? But this frontier, this makes life a little bit complicated. The question is, nevertheless, it's an operator. It's a relatively simple operator out of very simple energy. So does it have the same sort of estimates? To see what estimates one can expect, we do kind of the same numerology check as we had before. So if the p-Laplace is equal to divergence of f, we formally invert the divergence. This is, of course, extremely illegal. We cannot do this, but just for numerology. So what we would believe is somehow that a scaling somehow, right? This is essentially a scaling argument, right? So what we would expect is this conjecture, and was formulated by Iwaniec in 1983, is give me a p for the p-Laplace, not 2 maybe, and p equals 2, it's easy, but it's done. Assume we have a solution of this equation, a variational solution, uniqueness, and everything, and we solve in distributional sense this equation. Is it then true or not that the LR norm of the gradient of u is bounded by f, and now we have again that the gradient of u, right, to the p minus 1 may, that's kind of the best we can hope for, behave like f. And so, right, if you put an r here, then here we would have an r over p minus 1. That's a numerology that sounds reasonable, right? And then maybe we say this r, right, in this p equals 2 case, the r is larger than 1. So we would say here that r should be larger. This power should be at least p minus 1. And if p minus 1 happens to be less than 1, then we take at least 1. So this is the conjecture, okay? You want to have the LR norm of the gradient of U estimated in terms of the F norm LR over P minus 1 just because of this power here. Okay? All right, that's the conjecture. And many people, very famous people, worked on this, and this very roughly the state of the art, right? So especially Iwaniec had these results, Spadone, Di Benedetto, Manfredi. There's a picture of Manfredi, who is also at the University of Pittsburgh, and Tadeusz Iwaniec, Minjone, and many more, right? So I'm certainly not giving everybody credit here. But what more or less is the state of the art is if R is larger than P, so this is like for the normal Laplace, the case when R is larger than 2, you have this estimate, right? Now for the normal Laplace, you just do a duality argument. If you have the estimate for R larger than 2, you also get it for less than 2 just by duality. Okay, this doesn't work because this is a nonlinear operator, right? It's not somehow a self-adjoint-ish thing. But so you get this for R larger than P, and you can wiggle a little bit. This is this Iwaniec-Spadone a stability theorem. You can get this estimate for R, which is a little bit less than P. Okay, this is more or less the best we can do until today. So P and above we can do. P minus epsilon also works, but we have no real good control over the epsilon. It's very small. Right, it's computable, but it's comes out of a bunch of estimates. But then we have this sort of Calderon-Zygmund estimate, the gradient estimated by F in this norm. And the reason that we cannot do more somehow is it's a nonlinear PDE. We do not have a representation formula, right? We cannot write the solution to this equation as an equality. There are inequalities with Wolf potential, but we don't have a good equality, right? We cannot say gradient of U is equal to something. Okay. Now, what I want to talk about is how to disprove this Iwaniec conjecture when R is very close to P minus 1, right? Again, if P is less than 2, there's always this R should be larger than 1, okay? So I write here P minus 1, I mean more or less P minus 1, but at least 1. Okay, so this conjecture is wrong. And you will see the proof is relatively simple in some sense. It's a scaling proof. All right, so that's what I'm going to talk about. How to disprove this sort of conjecture, right? This sort of estimate when R is pretty close to P minus 1. All right. Now, the statement that I'm going to prove is this one. Fix a P. P is for the p-Laplace, okay? So P is not 2 because when P equals 2, we have Calderon-Zygmund, of course. Assume we have a number R. This is the integrability of this, of where we want to do Calderon-Zygmund, which is larger than 1 and P minus 1. And, excuse me, it's less than this strange number. For now, what we care about is this number. If this P is 2, this P minus 1 is 1, and we see that this number just adds up to 1. So if P equals 2, if we are in this Calderon-Zygmund case for the Laplacian, this here is just a 1. And if this is 1, there's no such R. Okay? So there's no number, little r, no power that we can do anything. But if P is not 2, you can check, this is just asymptotic argument, this number here is strictly larger than 1 and P minus 1. Right? And you can try to compute it, but, well, okay. So, statement is, if we fix an R, which is between this number, whatever it means, and that number, then we find two functions, they are Lipschitz, maybe you can even get them smooth, such that the LR norm of the U is larger than this norm of gradient U to the P minus 2 grad U, corrected by the gradient perp of V. Now, it will be in 2 dimensions for exactly the reasons that I can write divergence-free vector fields very nicely. Namely, I write here this gradient perp of V. All this means is this is the rotated gradient minus the y direction, the x direction, this is divergence free. So when I compute the divergence of this guy here on the right-hand side, right, this here doesn't do anything to the divergence. It just adds to 0. So if you fix a lambda and you find a u and a v, this depends on that lambda, right? For any u and for any lambda, there exists a u and a v, which are Lipschitz, such that this norm is larger than this norm. What this essentially says is if you choose f, the right-hand side, to be this guy, right, you have solved the p-Laplace trivially, as the p-Laplace of u equals the divergence of f, because this here doesn't factor, but the norm of the f is relatively small, and the norm of the grain of u is pretty large. So you have the counterexample to Calderon-Zygmund. Okay, so this is the statement we are going to prove. Right, and again, for p equals 2, this is an empty statement. There is no such r. For p larger than 2 or less than 2, you can compute this r exists. All right. All right. Now, how do we prove this? Let me start. So the techniques and the ideas of almost everything I'm going to say comes from convex integration. So I have a few slides on like the history of convex integration leading up to this result, right? So convex integration, again, my understanding, I'm certainly not an expert on convex integration, starts with Nash-Kuiper. So it's this isometric embedding theorem. Assume you have a torus. If you want to embed a torus into the Euclidean space, right, you want to identify these opposite sides here, this and this and this and this, well, you can do this by this old class Nash embedding theorem into a Euclidean space of very, very high codimension. I don't know what the codimension is, so something like n squared, right? So if this is whatever, right? So you can embed the torus, say in 4 dimensions or 10 dimensions, whatever, isometrically. So I want that the metric on this thing is the same in Euclidean space, induced by the Euclidean geometry as the original metric on the torus, right? That's the goal. Okay, so this is the first Nash result, right? This Nash embedding theorem was done first for these Calabi-Yau things by Calabi, and then by Nash. But then you can ask yourself the question, okay, can I still do it? Can I do this embedding in very low codimension? So in this case, can I embed this 2-dimensional torus into 3 dimensions isometrically? And this result by Nash, I think he proved it with 2 codimensions, and then Kuiper improved this to have just 1 codimension, is essentially this picture. So you take the torus, you embed it, not isometrically, because that's difficult, but you embed it topologically to a short embedding. So any distance along this thing is supposed to be shorter than the distances to the corresponding original guy. And then you add wiggles. So the wiggles are called corrugations, fine, right? And you add wiggles to increase the distance between points. So you increase the metric. And if you do this in a very smart way, the way that Nash and Kuiper did it, you actually end up, after taking a limit, with an embedding of the torus isometrically into 3-dimensional space. Now, this thing is not very smooth. This thing is, I think it's C1, but it's not C2, because you don't really have curvature, because then you could disprove this. All right? So you can isometrically embed the torus, this is what Nash-Kuiper shown, with relatively low regularity, right? C1 alpha for some alpha. All right, so this was the starting point. And then my understanding is that there was also this result by Smale, the sphere version type of questions. And Gromov took these ideas and let's say distilled them into what I understand is the H principle and this notion of partial differential relations. It doesn't really matter what it means for us. It's just, okay, that word appears. Now, this was kind of pushed into PDE by a paper. The relevant paper for this talk is this result by Müller and Sverak from 2003. They adapted these ideas of Gromov and ideas of Tata, to use convex integration to show like a funny result, which is related to this Hilbert's problems that every minimizer of a convex energy function is smooth. Well, the same result, minimizers or critical points of convex functionals in higher dimension, meaning in non-scalar U. So if U maps into R2 or R3 or something, this may not be true, right? Minimizers or critical points may not be smooth. This de Giorgi-Nash-Mortha technique doesn't work. And there is one example by Müller and Sverag, where they show there is a solution to kind of the Euler-Lagrange equation of a certain functional, which is Lipschitz, but it's nowhere C1, right? Even though this F is strongly quasi-convex. Okay, and again, this is kind of related as, or I like to think of this as a version or a counterexample, very striking counterexample to Hilbert's 19th problems for systems, right? They're true for scalars, but then for systems, this becomes complicated. All right, so we have this Müller-Sverag result, and then Faraco came and kind of used those ideas and introduced these staircase laminates. They won't play a huge role for what I'm doing, but they are kind of behind everything what I'm doing. All right, so now we are at Faraco. And for example, Faraco and Astala and Schikorra used this to get like Calderon-Zygmund type estimates. So here's one example. This is, I don't know, the 2008, right? So look at the PDE of the type divergence of A grad U equals 0. If A is not in BMO, but it's just bounded measurable, we have this Mayer result that says the gradient of U, if it's variational, is actually better integrable, right? So we get that the gradient of U is an L2 plus a bit, right? And that bit you can classify, there's a lot of results, but you also have this technique from, from convex integration by Asala, Faraco, and Schikorra that shows essentially a sharp exponent here, right? So you can estimate if A wiggles between 1 over k and k, you can find such an A such that the solution is not better than L2k over k minus 1 on any scale, right? This is this result, right? So you see this has a bit of a flavor of Calderon-Zygmund type theory for when A is kind of, this bounded measurable, but not regular, right? Not BMO type functional weight or thing. Okay. But the thing that came after that, and that is certainly most closest you will see to what I have, is this related conjecture by Iwaniec and Spodone from 1994. So what they proved, they disproved this conjecture, and so let me talk about this conjecture. It looks very similar to the conjecture I'm talking about. We look at very weak solutions to the p-Laplace, okay? So look at this divergence grad U p minus 2 grad U equals 0, but assume that a priori you only know that U is W1R, where R is pretty small, right? If you think about the distributional formulation, right? You have this gradient U to the p minus 2, gradient U, gradient phi equal to 0 for any test function phi. This makes sense when gradient of U is in W1 p minus 1, right? When the gradient U is in LP minus 1. So you can talk about this sort of solution. It's a non-variational solution. And the conjecture by Iwaniec and Spodone was, if this is the case, like this wild type of lemma, the solution is actually W1P. So it's a variational solution. And this is wrong. And this is this result by Colombi and Tione, very recent. And it's kind of the same. I mean, you will see it's very, very, very similar. Kind of same type of result. What we knew before this result by Colombi and Tione is that when we know that this R is very close to P, this is true. But, well, the open gap was what happens when R is very small. So the conjecture here is wrong, right? When R is very small. And you see the conjecture, I wrote the conjecture I'm talking about, it looks very similar to what we are having, right? So you see the difference is here I have a right-hand side, and this is kind of the important part, I want a variational solution only, right? here I have a solution which will be non-unique. It's not variational. And I want to know if it's solves the p-Laplace equation equals 0, then I have regularity theory. What I want to talk about now is even if I have a very nice solution, right? In our case, it would be Lipschitz, the Calderon-Zygmund theory still fails. So clearly these two conjectures are extremely related. And if you see this theorem by Colombo and Thione, you think, okay, this must be wrong as well, right? And you just try out to kind of adapt their techniques to this situation. Again, formally, they are kind of almost the same. Just take f equal to 0. But the important thing is we want a variational solution. Okay? So I want to talk about this thing following ideas of Colombo and Thione. Okay, so we want to use convex integration, but I promise you we don't actually use that much of convex integration. We really just use 1D calculus and a bit of linear algebra. That's kind of the cute part. So we don't really use the full force of convex integration. We do some estimates with 1D wiggles. All right, so here's the kind of crucial lemma, which I assume everybody can solve or prove. Fix 3 numbers, A, B, and C is in the convex hull of A and B. Okay, so C is a convex combination of A and B. I want to find a map F just from 0, 1 into R that globally looks like it has the slope C. But actually it only has the slope A or B, and it has the slope A exactly lambda times and B 1 minus lambda times. And this thing should be Lipschitz. All right, even piecewise affine. So what's the solution to this equation? Right, this is a triangle. Okay, I have a nicer picture, slightly nicer, right? If C is 0, for example, so you find a global, an affine linear map, such that F looks like it has slope 0 if you look at the boundary, but actually it has this slope or that slope. So in this case, the slope 3 or minus 1, and you can compute exactly on what size of set it has the slope 3, and on what size the slope is minus 1. All right, so that's very easy. Now the next step. You may not want that this globally looks so far away from this line, constant 0 in this case. So you want to kind of reduce the amplitude. That's also easy. You just repeat this construction a few times. So if you want to lower the amplitude, so you want to say uniformly close to this Cx type slope, you just repeat this, do a lot of triangles, and then you get this sort of result. You fix a delta, you find a map F, which looks globally like it has a slope Cx. The boundary is equal to C times x, but it stays arbitrarily close to Cx, but the derivative is either A or B, and this works whenever A and B have C as a convex combination. And you know exactly how many times you are A and how many times the derivative is B. Okay? So that's essentially the analysis that goes into this. All right, now we talk about systems, right? So we need to kind of lift this to higher dimensions. So how do we lift this to higher dimensions? Well, the only thing that you kind of do is you take this F that we have constructed here, these triangles, and you kind of push them to higher dimensions. So you look at F, you take X into a certain direction V, that's a vector, and you multiply F with the direction W. That's a vector of another dimension. Now it gets a little bit, okay, there's a little bit of a covering argument, so I'm cheating here. But essentially, I hope you can believe me, just by computing another derivative of this guy, the gradient, you see there will be this tensor product V tensor W coming out of this gradient. And hopefully you can believe me that if you now have 3 matrices, A, B, and C, C is a convex combination of A and B. And it so happens that A minus B is this tensor product that we get out of the gradient, so V tensor W, right? Then you find, with a bit of a covering argument, an affine map, still piecewise affine map, so a bunch of wiggles in a bunch of different directions, such that globally G looks like C times X, right? This is now a matrix product, fine. G is pretty close to the line Cx, right? Just like in the one-dimensional case. But the gradient of G is either A or B. Now, it's not exactly A or B. It's pretty close to A or B, right? But you know exactly how many times each of this happens. Okay? So now we have this n-dimensional version. Whenever we have the matrix C that we can write as a matrix A, convex combination as A and B, we can actually make sure that we have a G which looks like C of X globally, but the gradient of G is either A or B. Now, we can do this for 2 points, A and B. So this is my illustration of this result. If you have A and B in this matrix space, which is now very high dimensional, and you find C as a convex combination, and all we need is that the rank of A minus B, so this line, should be one-dimensional. Okay, so rank A minus B must be 1, then it's this tensor product, and then we can run this argument. Now, we have a G whose gradient is either A or B. Assume now B can again be written as the convex combination of 2 other guys which are rank 1 connected, right? So something like this. I have a D and an E, and B can be written as a convex combination of E and D, and again, E minus D has rank 1. Then, whenever the gradient of the original G was A, I leave it, but whenever it was B, I can replace it with this guy. Okay? Because at the boundary, this G looks exactly like B. And so I can now find a new function, a new map G, whose gradient is either A, D, or E. And I forget about the B. Okay? All right. So for now, I guess 3 guys, A, D, and E, I find an affine linear map such that the gradient is either A, D, or E. What I have to be able to do this is I have to write first some C is A plus B as a convex combination, and this must be rank 1 connected. And then this B must be a convex combination of D and E. Again, these have to be rank 1 connected. So this is not possible for all matrices, but they have to be always these rank 1 connections. Then I can do this, and again, I know exactly what probability I see that the gradient of G is essentially A or D or E, right? I have these things which just come out of the linear algebra that I have here, right? These convex combination things. All right, I can do this now for 3. I can do this for finitely many, right? So this is called this basic building block somehow in this wiggle. I don't know who this is due to. Müller and Sverrak say this is known. So assume we have a sequence of matrices. Let's call them dk now. Finitely many. And a bunch of like these convex combination weights, lambda i's. And we can write a matrix C as the convex combination of these dk. And in addition, we have to be able to do the construction that I just described, right? So we start with C, and we write it as the convex combination of 2 guys which are rank 1 connected. Then this guy we can write as a convex combination of 2 other guys, and so on. If that is the case, we find a map G, which globally looks like C times X. It is arbitrarily close to C times X, but the gradient of G is this dk exactly lambda k times. Now, we don't want always to say we want to do this construction with this decomposition by rank 1 matrices. So this is called this laminate of finite order. Like this here is called a laminate of finite order if I can decompose the matrices in this way, or I can construct them in this way. I start with C, do a convex combination of 2 rank 1 connected guy. One of the sides can be further decomposed in 2 rank 1 connected guys, and so on. This is called a laminate of finite order. Okay? And this kind of decomposition is called elementary splitting. Okay, these are just the words. What we keep in mind is whenever we can write a decomposition of matrices this way, we can find a G whose gradient we have prescribed. And that's what we want to use in an intelligent way. All right, so what's the idea of the proof of the theorem? Well, somehow we need to find a laminate of finite order. I want to have zero boundary data, so I put zero on the boundary. So globally it should look like a zero. I want to do some elementary splittings, and somehow a bunch of them should be good and only a few of them should be bad, right? That's a simple enough thing, but we have to decide what is good and what is bad. All right, so what is good, what is bad? Now, we want to solve this p-Laplace equation. And what we want to prove is that the integral over the gradient u to the p minus 2 grad u, this should be small, sorry, this should be large, and this here should be small, right? That is good if that happens. It's good if this correction of the gradient u p minus 1 minus this divergence-free guy is small, and at the same time, the gradient of u itself is large. Now, so what does this mean? Well, we can write this. First, we write our matrices in diagonal form. That simplifies things. And then we just look, what does it mean for this guy to be zero if I want my G to be, so my G in what I had before is simply UV. Okay? And now I compute. When do I know that this is zero? And it's a computation, right? What you see is, what you need to know is that this expression here is, I go to diagonals for simplicity. This is just z, and this is this negative to the p minus 1. Right? If this is true and the gradient has this form, you see that this here is zero. Even though this gradient of u itself can be whatever it wants to be. Right? Once this matrix has this structure, this is zero, and this can be large. So that's what we're going to call a good matrix. Okay? So we want to see a lot of this structure, and very little of the opposite structure where this negative sign is not there, because then this is not small. All right. So, lemma, we can do this. This is the construction. Fix a B. That's the weird guy. That's this guy from Colombo-Tion. Okay? We call these AIs the bad guys because you see they have the same sign. So this is when this gradient of u and the gradient perp of v kind of push each other larger. They don't compensate. Okay, this is what we call AI. And then we have a bunch of good guys, which is simply, so all we have here is that this and this are the same numbers up to the power p minus 1, and there is a plus sign and there's a minus sign. Plus sign, minus sign. Okay, so if they have different signs, and this is the power p minus 1 of this, we like that, and they have exactly the same weight. Here, the bad guys are a little bit not the same weight because of this B. That's kind of the main idea. That's funny enough that this works. But other than this, they have this P minus 1 weight. And the idea is we can write zero as an elementary splitting, done finitely many times, into a bunch of good guys. Everything is computable, and two bad guys, AN and negative AN, which are these guys. All right. I want to illustrate a little bit how this is done. Essentially, this is now just linear algebra, right? And you can compute everything. Everything is very computable, and it's only linear algebra. So what do? We want to start with the 0, 0, and we want to do these elementary splittings. Well, one simple thing, we want to get this B in there, right? We can split 0, 0, 0 into a B and a negative B, and you see that the difference of these guys has rank 1. So that's an elementary splitting. We can solve a gradient. We can find a function g that globally looks like it's 0, but actually the slope is either this guy or that guy. All right. Now we just are unhappy with the secondary guy, the 0 here. We don't want this. So we just say we write this as a good guy, right? This is b, and then the same to the p minus 1, and a bad guy. Okay, and this lambda we just compute, right? The lambda depends on b, easy to compute. And the same thing we do with this. So we can do two further elementary splittings, and we have two good guys whose lambdas we can easily compute, and two bad guys. Again, the 1 minus lambdas we can explicitly compute. Okay, and now we just do this splitting further and further. We want these guys to be large so that the probability that we see them is small. So the factor in front should kind of go to 0 at a certain rate. So this bad guy, we decompose further in 2 steps. I will kind of skip over this. It's kind of the same idea. right? With a certain probability, we see a good guy, and then we have here rank 1 decomposition, and this we decompose further, and we see a bad guy again at a larger scale. But the point is, we also see a little bit of these good guys. And the good guys is where the gradient, if the gradient is close to this guy, essentially my p-Laplace is 0. So I like that this here happens a lot, and this here happens few times. All right. So now we have maybe an algorithm how to decompose this thing. And again, everything can be computed. And again, the whole point of this construction is that now we can we find a map G, which is essentially just UV, such that the gradient of this G is either this guy, this guy, this guy, or that guy. And when it's this guy, I'm happy. When it's this guy, I'm happy. When it's this guy, I'm not so happy. Okay? I'm happy because here, this means that this expression is 0, whereas this p-Laplace for these ANs is pretty large. Sorry, not the p-Laplace, just this expression, right? The size of the matrix becomes very, very large. All right, once I have this, I'm essentially done. Now, I want to estimate this thing. I want to show this is small. Okay? So I want to show this is small in comparison to this grad u to the p-1 itself. Well, I just decompose. Again, my G is affine linear, so I just go to a bunch of sets where I'm in the different regimes. So I go to the sets where I'm in the good case, then I know that this number is essentially 0. It's not actually 0, there's a delta and there's a bit of technicalities, but it feels like this is a 0. It doesn't matter for our estimate. So all we see when we estimate this guy is this expression when this gradient of UV is this bad guy. But this happens with a low probability, right? The gradient here grows like n, where n is like a huge number. Then we see that we have a power here, so we just compute what is the size of this guy, and we compare this with the probability that this bad thing happens. So we get the estimate, this expression is a small number plus this, and everything is computable. The gamma n, we can just compute, right? This is the probability, the iterated probability that we see the bad guys, which gets less and less. On the other hand, if I just look at this expression itself without the corrector term, this is at least 1, so this is at least whatever, some number. It's not 0, that's the point. So we have two inequalities for our example, right? And
Amir, I didn't see your screen. Did you share the screen? The screen seems to like, yeah.
Can you see it now?
No, I didn't see. I don't know others. Hanchan, have you seen the screen? It seems.
Yes, I see it. I see it.
All right, I just stopped sharing and then I start sharing again.
Okay. Yeah.
Let's see.
But maybe just me. Yeah.
How about now?
Yeah. Now it's back. Yeah. Good.
All right. All right. So we are in the situation. Sorry, this was the previous slide, right? I just decompose this integral into the good set where this number is essentially 0 and the bad set when this number is large, but I know exactly how many times it happens, right? And then I have two inequalities which kind of contradict each other. If I just can show that this number is small, right? So I have that the gradient of u is very large and this corrector term is small. So we cannot have that this here is less than that, right? We cannot have the Calderon-Zygmund type of estimate, right? And this is a lemma. Again, it's an explicit computation. It's done in Colombo-Tione. There's a very nice exposition of this by Kleiner, Müller, Shakledi, and Scheer. How to compute this probability. That's an explicit computation, and that's what Colombo and Tione use, right? This number grows like an n to this weird expression. Okay, so if this number r here is less than this weird expression, this product goes to 0 as n goes to 0. It's arbitrarily small, which means that this number cannot be less than this number, even times whatever, a large lambda, right? So for each lambda, you give me the lambda, I find you a u with this method, such that this inequality is not true. And this means that we have found an example of, the p-Laplace equal to this number, the divergence of this number. However, we don't have Calderon-Zygmund estimates. And this disproves the Iwaniec conjecture. And again, I like to stress, we don't use the full force of convex integration. We don't go to the limit, right? We just use these approximations to disprove this sort of inequality. All right? That's pretty much it. Again, whenever we have this weird factor, right, which you can just check is larger than p minus 1 and larger than 1, unless p equals 2, then we get this sort of inequality for a given lambda. And this proves that we can have Calderon-Zygmund estimates. All right. Thank you very much for your attention.
Any questions for Amir? So, yeah. Hi, Connor.
Hi. Yeah, I have a small question. So you can correct me if I'm wrong, but it doesn't look like that the method is too dependent on the precise form of the nonlinearity.
Correct.
Like if you put divergence of g of mod gradient u times gradient u, and g has some p minus 2 growth or something. Is
yes. I kind of have the feeling you could argue maybe on some assumption you don't maybe want an x dependence, right? So something like x grad u might be a bit more difficult, right? Mm-hmm. But in principle, yes, it's just about the growth of the nonlinearity.
Mm-hmm. Okay, thanks.
Any other questions? So I have like a very silly question. You mentioned that there's a stability estimate, right? In other words, R close to P minus epsilon, right? You
yes.
also have this. You also have this number, like this number. How those two numbers relate? Okay, I see.
This one you can explicitly compute what it is. I don't know what it is. It's not super small, but it's. It's a number less than p minus 1. This epsilon is really small. So there's a huge gap in between, right? And that's still, that would be very interesting, right? We have essentially no progress going below this p minus epsilon, but there's no way that they are the same, right? There is a gap, right? And it's not clear what happens in this case.
Okay, I see.
Yeah, I have also silly questions. Because your technique seemingly needs a dimension to be 2.
No. It makes life simpler, right? So here's the simplest thing. That here, right, I can easily write down. It just has 2 entries. I did, I got interested in convex integration, and then I just tried things out. But so you can do this with differential forms, right? If you go to higher dimensions, you want to kind of like to write this as a differential form and think about this guy. And this gets a bit annoying with the with the entries. Mm-hmm. I think it should be doable. And I think it would also be interesting because the question is, how does this guy depend on the dimension? That's a bit unclear. Right? Mm-hmm. If the dimension is 3 and 4 and higher, does this exponent improve or does it stay the same? So I'm pretty sure you can run the same argument in any dimension, but it gets more and more unpleasant to do computations and hope that they are sharp somehow.
Mm-hmm. Mm-hmm. Yeah, and the second question is that the exponent with the b terms that there, it comes from the method, right? Is it expected to be kind of sharp for this sort of?
I really don't know. I didn't spend super long time, but our techniques that we have to prove Calderon-Zygmund are really restricted to this. Why do we have this epsilon? Essentially, what you are saying is the reason for this is that if you look at this expression and compare it to the best thing, which is a gradient, you can estimate this by an epsilon. ish thing, right? So you can do Hodge decomposition almost, right? You have an error factor. And that error factor, just you absorb things, right? So that's epsilon times a huge constant, which comes with all sorts of regularity estimates. That epsilon is tiny. It must be very, very tiny. And so I have no idea if this is optimal at all. And I don't see that this would improve somehow. Maybe that would be the way to go, right? To think if I have somehow that this tells me how the gradient should behave, and if I don't have this, something here improves, but I have no clue whatsoever.
Thank you.
Any more questions for Amir?
So what do people believe what happens between p minus epsilon and this number? I mean, is there a conjecture, or should it be or not? Or?
I also don't know. I mean, Iwaniec was very, very convinced that it goes all the way down to p minus 1. So I guess now it's everybody's guess, right? So the expert in the field said, oh, must be true for any r larger than p minus 1. The formulation is really very, very assertive. So I don't know what the conjecture is. What would be reasonable? We just have no techniques so far to go higher here or lower there.
All right, thank you.
Any other questions? Okay, so if no question, let's thank Amir for a very nice talk. Yeah.
Thank you, guys.
Okay, yeah.